Good afternoon. Can you hear me?
No.
Okay. I guess not. Can you hear me now? You know, I could just scream because we give lectures all the time, so how about we do that? Okay, so good afternoon again with a louder voice. So today I'll give you a little bit of insight about this new program that we launched at MSU. We call it Canvas. So it stands for Connected and Connected and Autonomous Network Vehicles for Active Safety. The talk is not really primarily about Canvas, but really to give you an insight, and maybe it's like a 10-minute tutorial about autonomous driving. So I wanted to start by this very interesting quote from an article that was published about a year ago, and is still probably very relevant in IEEE Spectrum magazine, which is one of our flagship magazine of our professional society. You could see that basically the title of the article, Self-Driving Cars Will Be Ready Before Our Laws. Before our laws are. Now, the subtitle will say, putting autonomous vehicles on the road is not just a matter of fine-tuning the technology, which is very true, of course. In fact, I think still a lot of fine-tuning needs to be done to the technology before we're really ready to roll out autonomous driving. So with that, I wanted to clarify a couple of jargons that used a lot, and we need to distinguish between these two areas, autonomous vehicle and connected vehicle. Sometimes they're used, frankly, interchangeably. But I think most of us recognize there are two distinct areas. I just want to make sure that we clarify this and just figure out where we're heading with each area. So, of course, with autonomous vehicle, basically, we're talking about a vehicle that has enough sensing capabilities and have enough really brain power, computing power, to sense and perceive its surrounding, and also is capable of making decisions and maneuvering around that surrounding. So that's really autonomous vehicle. Now, when you talk about connected vehicle, really it's a vehicle that is capable of communicating with other vehicles or with the infrastructure. This is where we hear the word V2V or V2I, vehicle to infrastructure. So these two areas are really kind of emerging and being developed rather independently. And the two areas are going to emerge and converge, hopefully, through this thing which we call it CAV, or Connected and Autonomous Vehicle. Now, all of these three areas, regardless how they're going to converge or if they're going to be developed independently, they will be driving the future of mobility. So those three areas, connected vehicle, autonomous vehicle, and the third one, which is the convergence, they'll be driving mobility. And you hear a lot about mobility. Mobility, or the future of mobility, will be driven by these, different technology areas. Okay, so one very quick thing I want to mention. In fact, many of companies, for example, if any of you was in the auto show and listened to the Google's self-driving vehicle program, the CEO who was giving the talk, talked about autonomous driving, all the technologies, really did not mention a word about connected vehicle. So I think we need to work a little bit hard on bringing these two technologies together, because I believe it's very pivotal to really have those two areas come together. I'm going to start a little bit of this tutorial about what does it really take to build an autonomous driving vehicle. So this is very high level. I'm not going to get into too much technical details. So the first component is really the sensing part. Okay, the vehicle has to have state-of-the-art sensing modalities. I'll talk about that. It's basically the idea to have 360-degree sensing around the vehicle. This is sometimes why we say we're going to have superhuman type of sensing, because it's really way beyond what even a human being could do, right? So that's the sensing part. Then we have the perception part. The vehicle, once it sends the data, it has to recognize the objects around it. There could be other vehicles, pedestrians, and there could be another higher level of perception. Perception is a word that's used a lot in computer vision and robotics, and basically it's an indication of you have to have some kind of brain power to recognize your surrounding. And then, of course, last but not least, the vehicle has to make a decision once it recognizes and perceives its surrounding, what's going to do with this information. Does it stay on the same lane that's driving at? Is it, it's going to change lane? Is it going to stop? Is it going to, speed up, whatever. So collectively, these two components, the perception and the decision, they really constitute what we call the brain of the autonomous vehicle. And we probably heard a lot about artificial intelligence. This is where artificial intelligence basically resides in that architecture. Last but not least, an autonomous vehicle going to need to have some kind of localization and mapping capabilities. It has to know what is localized within its environment. Is it really centered within the lane? Is it crossing the lanes? How far it is from a particular building or landmark, and so on and so forth. Some of this thing is kind of synonymous with the navigation capabilities we have today, but it's really much more than that. I'll show you some examples of what an autonomous vehicle localization and mapping will look like. So far we have an autonomous vehicle, but we could add this communication aspect, and then it becomes connected an autonomous vehicle. So that's the communication aspect that we add based on V2V or vehicle to vehicle or vehicle to infrastructure. Now, as you see, I'm putting actually the communication aspect feeding the brain part, because that will help the vehicle to make better decision about how to drive autonomously, or even actually improve some of the perception. In fact, in MSU, we are working on that. How could some of the communication aspect actually help even the perception and understanding of the surrounding of the vehicle? So the green part is autonomous, and you could see the theme color here is green for obvious reason, right? Okay, so that's kind of the, if you will, maybe 10,000 feet view of autonomous driving. I'm going to try to go over each of these components a little bit and give you a little bit more insight about it. So in the sensing part, this is actually a true vehicle. This is the Canvas vehicle. It's a research platform. We've been using an MSU to actually develop new algorithms and develop different technologies associated with autonomous driving. And these three sensing modalities, cameras, of course, is an important component. Radars, the vehicle, and most of the autonomous driving vehicles, they're equipped with radars, including the ones that on the road right now with even autopilot capabilities, for example. And of course, the new type of modalities, which is based on laser, which we call it LiDARs. So collectively, these modalities right now, there is a very consistent consensus, if you will, among major players within industry and academia. These three sensing modalities is going to be playing a major role in enabling an autonomous car, a self-driving car, to actually sense its environment. So again, the idea is to provide this 360-degree sensing capability, depending on which modality they, be doing different things. One of the things I should mention that these different modalities, they have their own limitations. And hopefully, if we get together in some other talk when we have a little bit more time, then we could get into what are the limitations of these different modalities. The other part is the perception. This is actually an example of what we call the deep neural network. This is an artificial intelligence that we're actually using in the Canvas project in MSU to help the vehicle perceive its surrounding. And this specifically actually basically doing vehicle detection and recognition and estimating distances from the car itself to other vehicles around it. I'm showing a picture of a simulation because an important component of doing artificial intelligence is actually basically teaching the vehicle to drive. So there is the learning component is a very important part. The more we drive the vehicle, I always say that basically an autonomous vehicle is almost like teaching a teenager how to drive. In fact, it's more like teaching even a 5-year-old how to drive. So, we need a lot of growing up, if you will, to make the vehicle, learn how to drive. So just to give you an idea, this is a scale. This is kind of part of the brain that we need to put in this vehicle to make it, capable of being autonomous. So that's one example. This is actually the example associated with using LiDAR, the laser, to develop very detailed 3D maps around the vehicle. If I could play the video there, please. I think you need just to go over, if you could put the mouse on the top here. Just. So this is actually, we use LiDARs to drive around the MSU campus. Some of you familiar with the campus, this Bowman Tower, MSU library. We're going around the circle in that area. And basically, we're using LiDAR to develop this very detailed 3D map to help the vehicle really recognize its location. And the neat thing about LiDAR is it's basically laser point, precision. So it's very, very precise. The vehicle knows exactly what it is, and it knows it's within, for example, a particular lane, and it's not crossing lines. If you have multiple lane, road, of course. So you could see the vehicle again. We have actually much more detail, and we're going to the MSU unit. So the second part, actually, this is also using the LiDARs. If you could play the video again, please. This is also to help the vehicle, and if you see, we're actually providing marking to the vehicle. For example, there is a crossing coming up, and the vehicle will be aware of that and be ready, just in case, for example, some students or pedestrians are, going to be crossing. So to get ready to stop and so on. And this is actually showing the trace of the vehicle. One of the interesting things, and this is probably potentially has some, some legal aspect in terms of, having the equivalent of a black box that we have in airplanes right now. Do you want, to have similar thing on vehicles to keep track of what the vehicle did? In this example, actually, the vehicle going to be taking a right turn, and ahead of time, we told it that the speed limit is 25, and there is a crossing coming up. So that's another example how, could use this technology. One of the major problems we're working on in MSU, actually, is trying to identify areas which is a little bit ahead of time. So, for example, driving on the snow, which is actually a huge challenge, not because of the slippery conditions, but also because you cannot see the lines. Virtually all of the autonomous driving technologies right now is based on detecting lines in the road and it's trying to stay within lanes. Now, in Michigan, we cannot guarantee that, right? So, and if you notice, a lot of the testing actually going on in California, San Francisco area, and in Arizona. I don't think they get much, snow in Phoenix. This is one thing actually we did. We got the vehicle to drive autonomously in this track just by basically using this. If you could play the video, please. So there you could see the vehicle actually will be staying within the track. And we did this during the very first snowstorm we had actually last year. And it was basically a whiteout. I mean, there was nothing, you cannot even distinguish, grass from, from the track area, from anything. And, the neat thing about this, really, the vehicle was very much able to stay in lane, using very, really simple, data and using GPS-driven information at the time. So this is the kind of problems also I want to emphasize that academia could play a major role in, which is identify things ahead of time and help industry, to basically, incorporate that technology into their future work. This is some of the other areas that we're working on in MSU under the Canvas initiative. I talked about, the sensing, but we're doing this multi-modality sensing where we're bringing the LiDARs and the radars and infusing their data. We have a very strong group in the radars area in MSU historically for many decades, in computer vision and biometrics, of course. So there are a lot of things MSU really can offer in this domain. One of the things I want to also highlight is we have these different levels and different definitions of autonomous driving. And there are a couple of levels right now defined, one of them by NHTSA, and the other one by the Society of Automotive Engineering. They're very similar, but just to give you an idea, basically where we are right now in terms of the cars on the road, they are level 1, and you could see basically you start from level 0, which is all human, controlled, all the way to what we're trying to get to, which is level 4 under the standard, or level 5 under the SAE definitions. So as we go toward the robot, then the robot will completely take over the vehicle and becomes fully autonomous. And for the Tesla, in both standards, actually, it sits what they call level 2. And in this case, basically, you're able to do highway driving, but as we know, the Tesla, for example, is not equipped to deal with urban environment. It cannot even detect pedestrian, for example. So just the importance of this thing is really the fact that we have a major challenge coming up, which is really the transition. Having a mix of these different capabilities on the road going to be probably one of the most challenging aspects of deploying or rolling out autonomous driving. Big question is, if a level 1 vehicle collided with a level 4 robot, whose fault is it? Is it the human or is it the robot? I mean, just an example, right? So this is one of the challenges. Another very interesting challenge that autonomous driving has is really the autonomy system has to become very much aware of its limitation. And, we're human, for example, when we're driving and it becomes, we say the expression, it's, raining cats and dogs, right? We cannot even see. We usually pull away and, we step on the side of the highway and, we stop the vehicle probably. I know I've done this many times, actually. So does the autonomous vehicle has to have that level of awareness when it becomes, basically aware of its limitation, like I cannot handle this thing, and what does it do about it? So, question is, do we need regulations about that? Another issue is the failure awareness. We talked about the sensors. These sensors are not perfect. And in fact, I could tell you right now, the pedestrian detection technology, at best, is probably at 90% to maybe 95% if we stretch it, accuracy. What are we going to do about the 5% that we have not perfected? I mean, is 99.99 is good enough in pedestrian detection? Or, how close we need to get to 100% before we say, okay, now it's safe, to do autonomous driving. So that's another challenge, of course. I wanted to conclude. Actually, I have many other things I could show you, but I think I don't want to hog the time. So I wanted to conclude by just highlighting, at least one of the benefits of autonomous driving, which is hopefully we could achieve some level of civility, right? So this is a quote from the same article. I look forward to having vehicles on the road that will actually let others merge. So, thank you.